Great, thank you, Kieran.
Getting technical issues. Good. All right. Okay, so good afternoon, everyone. So my name is Robert Clay, as Nick has so kindly introduced. I am here as part of the Uni of Leeds to present my work under the DUSH group, which is towards estimating categorical variates in agent-based models using the reversible jump unscented Kalman filter. So I'm going to briefly introduce the methodology of this work, some initial results on application to the station sim model, and then brief discussion on future work. So I don't particularly need this slide. I think Kieran and Nick have both explained very well the need for categorical variates in agent-based models. So the idea that an agent in a train station could choose between exit gates A and B. So you can't perform arithmetic on A and B, obviously, and you cannot assume they're Gaussian in particular. So this results in a lot of traditional data assimilation algorithms failing. For example, the unscented Kalman filter is one such data assimilation algorithm. It's a semi-popular technique compared to techniques like the particle filter and the ensemble Kalman filter. It is very efficient, but in order to do this, we need to assume that any variates we are modeling are Gaussian distributed. And we obviously cannot do this with categorical variates such as exit gates. So we need some kind of further augmentation. And so the bulk of my work has been developing this so-called reversible jump unscented Kalman filter, the IJUKF for short. And the idea is to split this problem into two halves. So the first half is a filter selection problem. So we generate a list of unscented Kalman filters, each with a different combination of categorical parameters. And the aim is to scan this state space and search for the best fitting Kalman filter, the one with, in theory, the true combination of exit gates. The second half of this problem is a filter parameter estimation problem. So we are estimating the parameters of the unscented Kalman filter, namely Gaussian parameters and Gaussian positions of agents in station sim. So to do this, we're going to use two unscented Kalman filters in parallel. So the first is called a current Kalman filter. So at some time t, we have a UKF with some estimate of Gaussian variates, some estimate of positions, and some combination of categorical parameters, some combination of exit gates. So we will treat this essentially as a null hypothesis. We treat this as the best combination of gates that we know of. And these gates are usually calculated from some previous algorithm step or from initial conditions. So the next thing we do is we generate what's called a candidate UKF. And the idea is that this candidate will have the same Gaussian positions as the current filter, but we will randomize it to have some new combination of categorical parameters of exit gates. And this is essentially an alternative hypothesis. We are asking the question, is there a better combination of exit gates that provides a better fitting Kalman filter given observation data? So we step both of these filters forwards in time, and when some new observations come in, we assimilate them both as normal, but we also perform what's called an additional reversible jump step. And the idea here is to compare the current and candidate UKFs. We want to say which one fits the data better. And to do this, we use an acceptance probability borrowed from reversible jump, Markov chain Monte Carlo. And the idea is essentially to calculate a ratio of likelihoods that determines which is better. So in this case, we can clearly see that the candidate filter appears to be closer to the truth, closer to the observed data. And so what we would do is we would reject this null hypothesis, and we would assume that this candidate filter has the best combination of exit gates currently. So we replace the current filter. We have this new null hypothesis, this new best combination of gates, and we repeat the process again. We generate a candidate filter with new gates. We step them both forward and assimilate, and compare them to find the best. As we repeat this over the entire station sim model run, we expect that this algorithm will scan the state space, will scan all possible exit gate combinations, hunting for the best one, while also assimilating in real time, so incorporating new data into these Gaussian position estimates. This also has the benefit that this algorithm is designed to be as efficient as possible. So we've used only two UKFs here. We could, in theory, use more and expect quicker convergence to the true exit gates. But this is designed to be in line with the vanilla unscented Kalman filter, which uses the bare minimum number of ensemble size. So just to show some brief results for application to Station Sim. First up here, we have a single model run of Station Sim. So we ran a model with 10 agents, and we have 2 plots here to show for 3 agents in particular that we've cherry picked to exhibit the characteristics of this algorithm. So on the left, we have position estimates for our agents. The solid lines are the true locations of our agents over time. And the dashed lines are the RJUKF predicted. And on the right, we have the exit gate choices for each of these 3 agents over time. So it can either choose to go to exit gate 0 or gate 1. So in this scenario, we have 3 typical cases of agents. So the first is the good case, where the agent very quickly finds its correct choice of exit gates, and so the position estimate is very good. This is essentially the perfect scenario, and the lower bound, whereas it's just our original unscented Kalman filter, and it proves that the RJUKF can indeed find the correct exit gate. So the second class of agent is the poor case or the bad case, where the agent cannot find the correct exit gate very quickly. So that is the green case here. And you can see that the position estimate deviates quite largely just because it's going the wrong way. And this is a problem. We need to try and address this in future work in terms of more quickly finding correct exit gates. So the third case is the ugly case or the mixed case, where the agent is contentious. It cannot decide between gate 0 and 1. And you can see it oscillating quite quickly between the 2. And as a result, the position estimate tends to compromise. It tends to aim straight down the middle until it finally realizes where it's going and corrects this. So this is the vast majority of agents behave this way, and it is a good sign. It shows that the RJUKF is indeed scanning the state space as we desire, and it is indeed able to adjust and find the correct exit gate over time. So we can scale up this analysis to many Station Sim model runs. So in this plot, we vary 2 parameters. We vary the population size. So more agents is more nonlinear behavior and more uncertainty. So we have 10 to 30 agents here. And we also vary what's called the reversible jump window. So that is, how often do we perform this reversible jump step? As we increase the step size, we expect slower convergence to the true combination of exit gates, if at all. So we run 100 Station Sim model runs here, and we calculate what's called the exit gate error metric. And this is simply for each agent. If the agent is going to the correct gate, we assign value 0. And if it's going to the wrong gate, we assign value 1. So we add up these values for each agent over time, and we take the mean over 100 model runs to get these curves here. And what we expect with this error metric is it will be bound between the number of agents above, where no agent has the correct gate, and between 0 below, where every agent is going to its right gate, the perfect case, essentially. So we can see as we increase population and jump window size, we get fairly uniform increases in overall error. And in the 30 agent case here, we see around 50 to 75% of agents are correctly finding their exit gate in time before they leave the model. So these are mixed results, I think. It shows that the filter does indeed seem to work, but it does not seem to be finding the correct exit gates fast enough. And I think future work needs to be developed towards improving the speed at which it scans the state. So to summarize, we've presented the reversible jump unscented Kalman filter, the RJUKF, as a means of simultaneously estimating both Gaussian and categorical variates in real time. So we presented brief application to Station Sim and seen mixed results, but a lot of potential future work is available. So first of all is methodologically. So as I said, we need a means of scanning this categorical state space quicker. Techniques such as Hamiltonian Monte Carlo are designed specifically for this, and I think would be interesting to implement to try and see the efficacy improvement. Speed improvements are also a big thing I think are necessary here. So the model is currently written entirely in Python. I think implementation in, say, C would be beneficial in terms of real-time application viability, but also in terms of scalability. So can we use more than 30 agents? And so finally, we want to try and apply this algorithm to real data, to the real Station Sim Grand Central environment, and say, okay, can we further generalize this to any combination of Gaussian and categorical states?